Hey friends, I am Scott Hanselman, and we are continuing our series of Stephen Toub types. When last we met our hero, we learned all about await and async and had a lovely time. And if you haven't seen that video, I'd encourage you to go back and check it out. For this video, we wanted to talk about regular expressions, and I feel like that is going to be a multi-layered conversation.
It's a fascinating topic. It's one of those things developers love or hate or both. But regular expressions to me are just an incredibly useful tool, both in code and just as part of my daily life as a developer. And it's a tool that I didn't learn at the very beginning of my career. I learned about it a little bit into it, and I feel like it was a lost opportunity. So, maybe helping others to learn about it earlier and see what it can do for them and how it shows up in .NET and the ins and outs and intricacies. And you can have a long conversation about it.
Yeah. A couple of things to kick off the conversation. First, I think people have an unnecessary fear of regular expressions. There's this sense of, it's almost a joke. Like they're a nightmare, they're impossible to understand. That can be argued one way or the other. There's the classic joke of you had a problem and you're going to use a regular expression to solve it.
And now you have more problems.
Two problems. Exactly. That's the problem. Additionally, from an implementation perspective, it is a language within a language. It is tunneled inside of a string, just like SQL gets tunneled in a string. So you have C#, which has an implementation as a library of the regular expression language.
Yeah, regular expression, and there are many dialects of regular expression languages. There are some commonalities that show up across platforms and environments and languages that use them. So a lot of the core constructs end up being the same. But there was a really fascinating paper put out several years ago about just how ubiquitous is RegEx as a single language, and can you just take a RegEx from here and apply it there and there and there? And there are lots of subtle differences that show up, especially around the edges.
So when I first learned about regular expressions would be in school in the 90s, or actually in the mid 80s, early 90s. And there is this kind of classic implementation from a gentleman named Rob Pike. And regular expressions started in the 50s. But Rob Pike wrote this matcher, and he did it in C. And if I scroll a little bit, I think it'll fit on the screen.
Yeah, it's beautiful. It's like 30 lines of code or something.
Yeah. And it's just, I remember as a student just kind of staring at that and understanding it, but also thinking I would not be able to just write that from scratch.
And this is like at the core of regular expressions, the syntax that this supports, star plus whatever, period to represent anything. That's at the heart of every variant of regular expression language. And then there's a lot more that has evolved since. And in many situations, they're no longer even regular in the theoretical sense. Some of the constructs that show up in .NET's version of regexes are in fact representable in sort of that theoretical approach. But it's a fascinating topic, and there's not just one way to go about implementing them. In fact, there are actually 4 different engines beneath RegEx and .NET. There are lots of ins and outs. To your point about it being, I used a regular expression, now I have 2 problems, the classic joke. It is a language in and of itself. It's a language that you need to learn and understand. It's very dense in that you can express a whole lot in a short amount of space. But what it allows you to do, the ability to specify the kinds of searches that allows you to do so succinctly and so easily, is incredibly powerful, whether you're embedding it into your code or whether you're just doing something in Visual Studio with find in files or grepping at the command line or whatever it might be. You can very easily find things using the power of regular expressions. So they're incredibly useful to learn.
All right. So let's dig in. I think we typically dig in by starting with a blank Visual Studio.
Yeah.
Our canvas here, you've added using system.text.regular expressions. You've brought that in as a potential namespace for you to exploit.
I have. And that's where all of the regular expression support in .NET lives. And it all lives behind a single type called regex. And you can see, I guess this is probably a pretty popular regular expression since Copilot is offering it for me. But you can see I just said new regex, and I'm providing then as a string the pattern. To your point, it's a language embedded within another language. So I have a regular expression here, and I'm using the regex class to allow me to process this pattern. So if I just wanted to search for something containing the text ABC, I would express it like that. Or if I wanted to find something containing ABC or DEF, I could express it like that. If I wanted to find any number of A's followed by B, I can express it like that, and so on. There's a whole language here. And in fact, because regular expressions are so useful and so powerful, you see Visual Studio is giving special support to Visual Studio. Notice this isn't just all dark red. You know, that star there is showing up in a different color, and the bar for OR is showing up in a different color. So there's Visual Studio is recognizing that this is going to be a regular expression pattern, and it's offering it certain coloring. Beyond that, it also has completion support. So if you want to understand what's possible within regular expression, IntelliSense completion tells you everything that you can do and what it means, and offers assistance in
it is worth noting, though, that syntax highlighting in embedded languages, the idea that the editor in Visual Studio that notices that using is a keyword and makes it blue, and that new is a keyword and makes it blue, previously in previous versions of Visual Studio didn't introspect into strings and recognize that that's a regex.
And it used to be that when it was first added to Visual Studio, it did it based on context. So it special cased, oh, I see you're using the regex constructor, therefore I should treat this as a regular expression. But more recently, there's an attribute in .NET called string syntax, where you can basically attribute fields, properties, parameters, and say that this is a regular expression. And then anywhere that shows up, Visual Studio will offer similar support. And we can see this not just for regular expressions, but if I have string syntax attribute and I dot off of it, you can see a whole bunch of things offered here. These are the ones where something has some level of built-in support recognizing it. So is this a numerical format that I might specify as part of a string formatting, or XML or JSON? And you can see that in other situations as well. Like if I have JSON serializer dot deserialize, this is one of these is taking a JSON string. And if I look at deserialize, we can see that the ones that take a string are attributed as string syntax JSON.
Okay, so string syntax, this little post-it note, this attribute, this language attribute, that's the thing.
Exactly. And then
that it's looking at.
Visual Studio will see that. And if I start typing something here that would be JSON, so, key value, 2, 3, you can see I got this. This isn't just all red. I got the syntax highlighting that suggests that Visual Studio recognizes that this is JSON. And if I were to make a mistake in it, let me fix this error because this is going to override the other stuff. Deserialize this as, I'm going to make up something. It doesn't matter what I put here. If I were to make a mistake in this, then I get an error saying, I know this is supposed to be JSON, but this isn't JSON. You made a mistake. Go fix it. That's because of that string syntax attribute, which then also shows up for regular expressions. So right. If I had my own method here, and I just said string syntax dot regex, and I made this a string, then when I go to call M, I get that same syntax highlighting that we saw earlier because Visual Studio is just recognizing this.
And this is maybe not intuitive to folks that are using interpreted languages that are thinking that this is a parsing issue. When I showed that regular expressions article here with Rob Pike and Brian Kernighan from 20, 30 years ago, that was a very parsy time. It was Lex and Yak, and then you compiled your code, and it was your editor and your compilation experience were very separate. But here, you haven't even saved this file.
Right.
And line 5 is already being recognized as a regular expression. So because it's happening in the background, that it's blurring the line between what you're typing and what's really being compiled. And this DOM, this code DOM of sorts, is being introspected into. And people need to remember that there's things happening behind the scenes that make regular expressions expressible in this way on line 5.
Yeah, exactly. So back to where we were. So we had our regular expression. We were saying new regex. I think I had A, B, C, D, E, F. And then I could do something with this, right? So I could say, let's say I had some input from somewhere. And I wanted to see if this matches the text. Hello, ABC, how are you? And I just print out console.writeLine r.isMatch input. Because I'm searching for either ABC or DEF, this comes back with true because it found. I like that Copilot is telling me, yeah, this is going to be a match. That's pretty funny.
Did you run this, and did we not see that pop up?
Sorry, yeah, it popped up on my other screen. Let me do this.
Okay.
Console.readLine. Just give me a little opportunity to. There we go. So now we should see it. There we go. And I'll hit enter, and there's the true that comes out. So we were able to match.
So this line 6 here is very simple and easy to understand, because I think we can all agree that we recognize a pipe as an or. Mm-hmm. A lot of times regular expressions look like swear words, like in comic books, where it's just the whole top row with ats and hashes and all kinds of stuff. But this is a good basic understanding.
It can get pretty complicated because you need some understanding of what the different constructs are. So you mentioned a hat. So if I put a hat here, that basically says that I want this to only match at the beginning of this string. So if I were to run this, that would fail. It wouldn't find a match because ABC only exists in the middle, not at the beginning.
But does it also mean that DEF should also be at the front, which you just answered?
Yeah. So, and if I'm going to group these things together, so there's some level of precedence. So if I put this, that still matches because this is interpreted as binding tighter than the or, as if I had kind of grouped these with parentheses. But if I instead did this, and now I run this, now it will fail because it's saying that the match has to begin at the beginning, and after that there must be either ABC or DEF. And these parentheses not only mean grouping, but it's a special kind of group called the capture group, which allows me to then subsequently, rather than if I just did isMatch, if I instead did r.match, I actually want to know what was matched, and I can look into it to see if there were any number of these parentheses. I can see what value came from a particular piece of it. So let's say I'm going to get rid of this. When I run this, I get ABC, but if I were to put another set of parentheses, say in here, and I'll change this to 2, what's happening? Oh, I forgot to hit read. I forgot I had that at the beginning. Now we see that it's printing out the capture that was in these parentheses here, the second one. So this was the first one, this was the second one, and it's printing that. So you can ask for information to be extracted from the overall thing that you're trying to match.
So let's try this. Let's pause and back up for a second.
Yeah.
Go back to ABC or DEF.
Yeah.
And if I were simply searching for ABC, I could do a substring. I could do an index of.
Yeah.
Actually, let's even back up further. Let's just do ABC.
Yeah. At
this point, is a regex overkill? And what is it doing? Is it just doing an index of or a substring to go and answer that question?
Great set of questions. So is it overkill? Depends on what you're trying to do. If all you were trying to do was say isMatch, if all I cared about was that, then yeah, I might as well have just said input.contains ABC, right? I could have done the exact same thing with input.contains ABC.
Okay.
And there's no,
Yeah.
this is you can't do better than this. This is about as good as you can do.
Well, and the fact that on my mind also, by the way, just as a point of note for our friends that may be coming to C# a little bit later, the fact that I went to in my mind for things like substring and things like index of shows my background in C 30 years ago, while .contains would be more appropriate.
And I could do that as well. I could do index of ABC index of, and just say, this is greater than or equal to 0. Culture issues aside, it would be the same.
I was just going to ask, though, contains has some culture awareness. Does the regex by itself have culture awareness as well?
Excellent question. Yes, but by default, the matches that are performed by regex are basically the equivalent of string comparison ordinal. There's no case insensitivity here. By default, unless I do something special, the match is case sensitive. And if I wanted this to match in some sort of case insensitive way, I could go and specify that myself by saying I want either capital A or lowercase a, or capital B, lowercase b followed by capital C, lowercase c. I could also say, I actually want to specify some options here, and I want this to ignore case, which is effectively what I said, capital A, lowercase a, capital B, lowercase b, capital C. But there are culture issues that come into play, especially if this wasn't ABC, but this was instead like ABCI.
Right.
Being a special
the legendary case. Turkish I problem.
And so this will match differently based on whether my culture info.current culture is ENUS or TRTR for Turkish and Turkey.
And just to be clear, you used the word ordinal. You threw that word out. But when something is doing ordinal, that's focusing only on the pure raw byte values.
Yeah, the integral value of the numerical value of the character in this.
Well, invariant culture is more kind of intuitive in the sense of like cultural differences matter, and I want to do a comparison while being somewhat aware of linguistics. Yeah. So worth noting. Okay.
So and this also highlights that there's a whole bunch of ways that you can configure how the regular expression, either how the pattern is meant to be interpreted. In this case, we're saying, I wrote ABC, but I really want that to be like as if I wrote capital A, lowercase a, capital B, lowercase b, capital C, lowercase c. It can also be instructions to the engine itself about how the engine should operate. So we can talk more about this, but there's an option, for example, compiled, which changes the engine under the cover that's being used. Semantically, it's the same. But implementation-wise, it's an entirely different implementation.
Okay, so let's talk about that. Which one allows us to introspect? Because my original question was, well, maybe I should just call contains or index of myself. If you did an ABC, how does line 9 execute? And can we see that?
Yes. So I'm going to answer your question in one moment. Let me first take a tour through what the engines are so that we can see where we get to.
Love it. Let's do it.
When I just wrote this, you referred to this as being a language within a language, right? And languages have multiple ways that they can be processed, but the most fundamental way that you can process a language is to interpret it. You are given the input and you parse it and you figure out what all the little pieces are and you walk through it and say, oh, I know what that means. Let me run some code to simulate that. Okay, I know what that means. Let me run some code to simulate that. When you write new regex, you don't specify any other options. You're getting an interpreter, which when you construct this, it parses this. And if I had something like A star B, it's going to parse that and to say, okay, I see two things here. I see a character loop around A, and I see a single character called B. And it parses this into a sequence of opcodes, one of which will be character loop, and the next one will be character. And there'll be an argument for each. So character loop with an argument of A, and character with an argument of B. And so it constructs for itself this sequence of operations, these opcodes. And then when you say is match, there's a method with a big while loop that contains a big switch statement. And it switches over each opcode, and when it sees opcode dot character loop, it jumps to that branch and it knows, oh, I know how to process a character loop, and it runs code for it, and then it goes back to the beginning of the while loop and it processes the next opcode.
Okay, so let me see if I understand. So you are writing on line 6 there in 3 bytes a program. You are expressing intent,
Yep.
albeit in an incredibly terse and specific and syntax limited way in 3 bytes in A asterisk B, a program.
Mm-hmm.
It then gets interpreted by the interpreted regular expressions engine, of which that's one of the engines. And it's going to expand, but I can't see that. I could go and look at the source code for that engine and maybe learn about it.
You could debug through it if you want to. If that would be a fun exercise, we could set a breakpoint and actually step into the .NET code that does it. But that's exactly what's happening.
But even though C# in this application gets compiled, if you were to do line 6 multiple times, 4, 5, 6, 10 times, it's going to treat it like it was the first time it had ever seen it. Every single time.
Now, if I do line 6, 7, 8 times, it's going to interpret like it's the first time each 6, 7, or 8 times. If I do line 9, 6, 7, or 8 times, it will when the constructor was running, the constructor will have parsed and done all the analysis and interpretation into the series of opcode. So it's just got that basically array of the program. But then it will interpret, it will run through that while loop with that big switch statement every time you call line 9.
Got it. Makes sense. Okay, cool.
Okay,
and so why would I ever pick that one over compiled? Isn't compiling always better?
You would pick this one over compiled if it was just this little throwaway thing that you were going to do once and never do again.
Okay.
Because it is very fast to get started. The constructor will run very quickly and then allow you to jump right in, and it'll do a reasonable job at a reasonable speed of performing the match operation. Where it falls down in terms of performance is when you want to start doing this over and over again. So I have my A star B here. If I just want to do it once, just use the interpreter. But if I'm going to do this on a hot path 1,000 times a second, I want that optimized as much as possible. I really want code that is specialized to this particular pattern. And that's exactly what a compiler does. It takes a program that could be interpreted if you wanted to, and generates specialized code. In the case of a C compiler, it would be assembly code. In the case of the C# compiler, it would be intermediate language, MSIL. That is specific to its input. So there is the option that we saw earlier, regex options.compiled. And what this does, what this engine does is when you construct this, it not only parses this and analyzes it and tries to optimize sort of the structure of the tree, but then it takes that and it uses reflection emit to spit out at runtime a dedicated sequence of IL instructions for processing this pattern. And that's all it knows how to do is process A star B. The interpreter can process anything. The code that this generates can only handle A star B, but it can handle it way faster. 4 or 5 times order of magnitudes, depending on what the exact pattern is. And so, but that process takes more time, right? We have to run a compiler effectively.
So it would be a mistake to do that once.
It would be a mistake to do it, once. If it's just a throwaway thing, it's not worth it. We're going to spend more time compiling than we would generating the match. But if we're going to do this a lot, it's worthwhile. So that's the compiler. Now, the other one, which is, I think at this point, those engines are both great, but by default, they're not the ones that I would recommend people use anymore. One of the things we introduced 2 new engines in .NET 7, which in general should be the go-to engines that folks use, and one of them is the one that answers the question you asked me before. So I'm going to write a little class here. I'm just going to call it partial example, and I'm going to add a method to it, a partial method that returns a regular expression, and I'm going to call it demo. Now, I'm not sure how many folks are familiar with partial in C#. But
partial's a really interesting one. Partial's fascinating because it's like part of it's here and part of it's over there.
Exactly. And that's exactly what partial allows you to do. It allows you to split the definition of not only a class, but even separate the declaration and definition of something like a method between two locations. So I can have multiple copies of this example class anywhere in my compilation unit, and I can add multiple member. Oh, this is static. So static. I can add multiple members to this type, and when it's compiled, it will be like I wrote them all in the exact same.
Right, and they can live separately a couple lines away,
Different
in other
files.
files, in entirely different assemblies.
Not entirely different assemblies. They can live in anywhere in the same compilation
scope.
Yeah, but
Gotcha.
when the compiler compiles it combines them all into this single class that's then ends up in the assembly. You can't do partial across assemblies. But the interesting thing about this with a partial method is I haven't provided an implementation here, but I can provide an implementation here. And now if I'm just going to do that just for example's sake, notice the squigglies went away. So I was able to define demo up here, and some other code somewhere in my project, in this case it happens to be in the same file, but it could have been somewhere else, can provide the implementation of this. And so I can use...
So is this like header files and C files?
It's very much what it's like. A header file in C, you define sort of the signature, you declare the function, and then somewhere else in your .c file, you provide the implementation of the function. And this allows you to use, I could say .count. This allows you to use it, and I still haven't provided the implementation. Something somewhere else in my project has provided the implementation. Now you combine that with source generators, and now things start to get really interesting. A source generator, in the context of a C# project, is a component that basically plugs into the compiler. And when the compiler goes to compile your program, and it generates the syntax tree and does the semantic analysis, before it's done, before it kind of takes all that and generates code, it hands it off to the source generator and says, here's what I've currently got. Is there anything you'd like to add? And then the source generator can say, oh yeah, add this file that I just dynamically created. And the compiler will take that, it will do the syntax and semantic analysis, it'll combine it all together, and then it will generate the program.
Okay.
Which means...
Does that mean that then the designers of the regular expressions engine can do some of the work for us, and then the source generator can do the rest of the work, and then everybody wins in the end?
So I can come back up here, and rather than me writing that partial implementation myself, I'm just going to tag this as generated regex, and I'll say A star B. And now you notice the squiggly went away.
Ah.
Why did the squiggly went away? Well,
because now there's an implied partial elsewhere.
Because the regex source generator spit out this regex generated file that contains the implementation of that method. We can see that method is implemented here, and it's implemented it by just returning the value of a static field. So there's a singleton that it's cached. And let me just bring it up next to the expression so we can see.
Yeah, and you'll need to zoom in a bit there.
Let me just simplify the expression to highlight what we're doing. So we searched for ABC, and that was our regex. And you were asking how it was implemented? Well, here's the implementation of the regular expression. You see that all it's doing is saying, find the next possible place. Oh, sorry.
I want to call out, I feel justified on line 85 there, if you can zoom in.
Yep.
In fact, one of the implementation details ends up being, in fact, index of.
Yeah, absolutely. That's what I was, you beat me to it, but that's exactly where I was headed is.
Sorry.
No, this is great. I love it. We can see exactly how it's implemented, and it's implemented exactly how you suggested it would be, which is the engine recognized that all you're doing is searching for ABC, and it can use index of to fully implement that. I can change this. Instead of ABC, if I searched for a character class containing A, B, or C, so this is just, rather than searching for A followed by B followed by C, this is searching for A or B or C, exactly as if I'd written A or B or C.
It's interesting implementation there, though. Where did B go on in line 85?
That's a great question. This is using a method index of any in range. So it's saying anything from A through C is valid. So if I were to, just go back to my character class representation of this, And I can do A, B, C, D, E, F, G, H, I, J,
What
K,
if you
L.
what if you did CBA?
Same thing. Because
Very
within a
clever.
character class.
Very clever.
But the moment I start doing more complicated things, this is going to change a little bit. So now if I were to just stay at a star after this, you note that things have changed a little bit. Now it's using index of any except in range because it's trying to find the first place that this doesn't match. So now it's saying, I want to find all of the, if I have ABC, 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 followed by D, it's looking for the D because it then knows that everything that came before that was part of the match. So it's using these built-in functions to optimize the processing of this regular expression. And this source generator is incredibly useful for understanding, to your point, how these regular expressions actually work. If I did ABC or DEF, go down here to the matching, you can see we're generating a match with two alternative expressions. We're switching over the first character because it recognizes that the first character of each branch is different. So if it's an A, then we're going to continue to match BC. If it's a D, then we're going to continue to match.
Please do zoom in a bit more.
Oh yeah, sorry.
Appreciate your patience. And it's important to note that while someone might, who's a little earlier in career, look on the right and say, wow, that looks very brute force, it looks very hard-coded, it's because it's okay for a source generator to do stuff that is incredibly specific, because that allows it then to be optimized, because it is in fact custom stuff.
Exactly. And the moment I change my source, the program updates. So we're just seeing a live view of what will be generated. And every time I compile, it's taking this and generating. In fact, every program you compile, forget source generators, every program you compile is taking your source and generating an output that is customized to exactly what you typed. That's the whole purpose of a compiler.
Right.
In this case, there's just intuitive, I think. Step. Yeah.
I don't think it's intuitive for people to think that that little tiny program, which in this case here is the letter A, that's a program. It's a regular expression. Now, I notice I do want to have a small aside, though. There seems to be a GIF versus GIF argument here. Is it RegEx or RegEx?
Yeah. So I think it's probably RegEx, hard G.
I feel like you're trying to be inclusive and you want to say RegEx, but you're also trying to support others.
It is regular expression. It would sound really weird if you said regular expression. However, the whole time since I learned about them, for whatever reason, I've said RegEx with a J. Yeah. So I realize that it's supposed to be RegEx, but I can't help myself.
I can't do it either. I've noticed recently also when I've been working with people who work in SQL that apparently Microsoft people say SQL and the rest of the planet says SQL, and I can't change it.
Yeah, it's really hard to adapt.
I also want to point out the tooling. Oh, sorry, go ahead.
I was going to say, I say both. Sometimes I'll say RegEx, sometimes I'll say RegEx. Yeah. So I'm inconsistent.
It's really worth pointing out also, just like in the old days, if I recall, and correct me if I'm wrong, 15 years ago, I would do this when compiled regular expressions first came out in C#. I would go and compile them, and I'd have to open up an application like ILDASM, and I'd hit Control-Shift-B, I'd compile it, I'd find the DLL, I'd open it up in Reflector, and I'd look at it. You're typing and getting this source generator source code instantly.
And not only that, I can, this is just source, dynamic source, but source in my project, which means that I can do things like set breakpoints. So if I search for ABC and I hit F5, we can see this little tiny build started, build succeeded, my program launched, and I hit my breakpoint, right? And I can step through this to see exactly how this processes like I could any other code in my project. The other, really neat thing about this is I may not have done it yet, but if I highlight this isn't just about sort of the generated source. This is fully part of my application, which means the source generator can emit things like XML comments. So if I hover over this, I can see at the usage site, for example, what pattern this is, right? This is a pattern that matches A. If I did A, B, C, or D, E, F, and I hover over this, we see this is a pattern that matches two alternate expressions, A, B, C, or D, E, F. So yes, this is a complicated language, but it's explaining it in regular English.
Yeah, that is really important and worth also just hitting a little bit harder, because that code on the right is well documented with thoughtfully named variable names. This could have been, I would have expected maybe it to be obfuscated in some way, but it doesn't need to be.
Well, I appreciate your calling that out, because I worked pretty hard on that.
Is that you right there? Is that your idea? Like,
yeah.
This matters?
So when we initially, here's the evolution of how this came about. We had the regular expression compiler that you get with regex options.compiled. Source generators came about, and we wanted to implement a source generator. So the logic behind the compiler and the source generator is effectively identical. The difference is, are you emitting IL or are you emitting C#? And the initial incarnation of the source generator was a line-by-line port of the compiler generating IL to the source generator emitting C#. So the C# that you got out looked like you were reading IL, because it was just what is the minimal C# we could emit to represent the exact same concept showing up in IL, and it results in very not readable or understandable C#. So we ended up in .NET 7 not only implementing the source generator, but we rewrote the compiler. We did them both in a way that not only made them faster, but also allowed for a representation that looked more like sort of idiomatic C#. And then once we did that, we could add comments, we could make variable names look good, and we could spend a lot of time making the code very readable, because it is part of your project. We want it to be something that people look at and understand and learn from and debug and maintain and whatnot.
How would you test this, and how did you not find yourself playing whack-a-mole with just awful edge cases at every turn? Because this is combinatorics at its worst.
Yeah, we have a very large test suite for for system text regular expressions, tens and tens and tens of thousands of different patterns with expected inputs, as well as some things where we're actually validating against known good, known bad inputs, or we're looking for this exact capture showing up in the input, as well as other things where we just validate that things compile and run and produce and are idempotent, produce the same output each time. So we actually, with some help from some other folks on the team, scoured every appropriately licensed nupkeg on NuGet and extracted from them the regular expressions that they were using, and built up a database of about 20,000 unique regular expressions. I say unique because many of them were duplicated many times. So there was something like 4 or 5 million different regular expressions that, or different cases of them, and they were deduped down to about 20,000. We actually made that available online. It's in the runtime assets repo because we use it in our tests, but it's just a big JSON file that shows all of them and their popularity. So we use that as part of our tests. Those tests run across all the engines. So we use it, we test it with the interpreter, we test it with the compiler. We also, in our test suite, take the pattern, invoke the source generator, compile it, load up the compiled regex, and then run that as well. So we're validating all of them against the same inputs. But you're right, there is a combinatoric problem, and there are invariably going to be, every once in a while we find an edge case that we missed. I just fixed one that we serviced back to .NET 8. I think we found maybe 3 of these in the last 2 years. But it was, it's always like, if you're using a lazy loop inside of a look around that has part of a capture group and it's got something following it that is like, then we missed fixing up the whatever, and it's always this complicated thing.
I've also thought that I seem to remember 10 or 15 years ago there being runaway regular expressions.
That is an excellent segue into the last engine that I did not mention. Yes, so whether you call them runaway regular expressions or catastrophic backtracking or RDOS, regular expression denial of service, let's work our way into this. So if I have a little expression here, I'm going to use the source generator so we can see what it's doing. And I just do A star B. There's this interesting word that's thrown into this explanation, and that is this word atomic. And that's there to differentiate from something that is non-atomic. So let's say I have the pattern, and you'll notice that if I change this slightly, and now I go look at it, it no longer says atomic. Now it says greedily. So by default, loops and these variable length constructs in regular expressions are what are called greedy. And that means that they try and consume as much as they can. So if I match this against A, this loop here, when it starts to run, is going to try and consume all of it. But then it's going to try and match what comes after it. It's going to say, I can't match. I don't have any more input. Let me give one of these back. So it's going to back up. Instead of consuming however many this is, 10 A's or something, it's going to say, okay, what if I just matched 9 instead? All right, well, then I have an extra A, and this can successfully match. And we can see that if we go and look at the source for this, down here in the matching routine, you can see it's matching A greedily any number of times. It's looking for the first occurrence of something that isn't an A, so it's blazing through in a vectorized manner as much as it can. And then it's going to advance to the next position, and it's going to try and match a character in the set A or B. Right? If that fails, you can see the word here, backtracks. And this is exactly, if you were solving a maze, your kids are at a restaurant and they've got the little thing in front of them and they're using the crayon to go through. It's exactly how you solve a maze, right? You start one way and then, I hit a dead end. Let me back up to the last point I made a decision and let me try the next one. Dead end. Let me back up. And so you're backtracking to the previous point you made a decision. And if you exhaust everything there, well, then you backtrack further. And so you're sort of exploring the full graph of what could be explored.
But help me understand, if you go back to the program, it's linear and you're at the end of the string and there's no cyclomatic complexity. It's just a linear string. Why back up? You've already consumed an A. Backing up is not going to give you a free B.
It's not going to give you a free B, which is why the analysis changed this to atomic, because it recognizes that there's nothing A star could have matched. That was a B. But when I change this to AB, there is something A star could have matched. That was this, which is why you now see, we can't automatically make that.
So it now knows it does need to back up if it is ever to satisfy AB.
Right. So the analysis engine tries to eliminate this looping, this greediness, this backtracking whenever possible. But sometimes it can't. And that backtracking causes this to be potentially much more expensive operation. Let's look at a little example of that, because it gets to the runaway thing you were talking about. So let me just create a little loop here. We'll go from I to some small value like 40. And now I'm going to create a regular expression. We'll fill in what it is in just a moment. There's going to be something here. And I want to time how long this takes to do various things. So let's
make this code a little bigger on the screen as well.
Right. There we go. Is that all right?
Yes, sir.
All right. We're going to print out the iteration that we're on and how long it took. All right. And then I'm going to do is match, and I'm going to match it against some input. So now we need to fill in what is this input and what are we matching. So the thing that I want to match is going to highlight the algorithmic complexity that you talked about. Let's say that what I was matching was, first I should explain what this is. So /W matches a word character. That's a letter, a number, anything that might make up a word. /D matches a digit. This is Unicode digits, so it's not just 0 through 9, but basically 0 through 9.
So let's use my password as the input, Hunter2.
Hunter would that whole thing would be both word characters, but the 2 is also a digit. Okay?
Right.
Okay. Now, let's say I put in an alternation here, but rather than word character digit, I do digit word character. Okay.
Oh, wow. Okay. It would need, if it got, okay, I'm starting to see where you're going here.
So I can match, if I put 1, 1, that will match both of these, right? Because 1 is both a word character and a digit. All right. Now I'm just going to put that in a little group. So I can do 2 different possibilities for how this would match.
Gotcha.
2 different things to check. Now if I say, okay, well, after that is matched, let me do it again. So now for each of these, I might have to do each of these, right? So 2 times 2, right? There's only 4 possible things to check right now. Not too bad. What if I do 3 of them? All right, now times 2. So now there's 8 possibilities. Times 2. Now there's 16. And if I were to just sort of, let me put a little $sign here. And I'm just going to put the iteration number here. In fact, let me make this 1 less than or equal to 40. All right, so now I'm looking for either 1 of these or 2 of these or 3 of these or 4 of these. And what we just saw from each time I added another one, it multiplies it by 2. This is now exponential complexity. 2 to the I.
So the question is, will you even make it to 40 iterations?
Exactly. So now let's do string.concat. And I'll do enumerable.repeat with 1, 1 and I times. All right.
So the string is going to get longer as well.
Yeah. These are all going to match and trivially match. So when I run this, let me do my little console.readline up here again. Console.writeline. Enter when ready.
Yeah. Cool.
All right. Now I run this. Where's my part? There we go. It's over here. Run it, no problem. Blazes right through it, super fast. Now let me change it a little bit, and I'll say I only want it to match when the match is the full input that I've given it. So it has to the match has to start at the beginning of my input, and it has to end at the end of the input. That's what these are. These anchors say. There's a beginning anchor and an end anchor. No problem. Again, I run it, blazes through it, but if I then come in here and just make one simple change, I'm just going to add another little 1 right at the end, which won't match because these things come in pairs. We start looking at how long this takes to run. You see it's doubling kind of execution time each step of the way. Mike, you don't know if you can hear it, but my CPU has started, the fan just turned on. Because, it just took 5 seconds to process just 25 characters. And it's taking 11 seconds to process just 26 characters. And that's because this exponential complexity of basically 2 to the n with this pattern. So this is one of the reasons that there are multiple kinds of regular expression engines. There are ones that are implemented with backtracking, and there are ones that are implemented without backtracking. The .NET engine, the Java engine, the PCRE used by Perl, the one used by Python, they're all JavaScript. They're all backtracking engines. Go with RE2 and Rust with its Rust crate for regex, they implement a non-backtracking engine.
On purpose. That's a decision someone made.
Exactly.
And are they saying backtracking is too dangerous to be escaped?
Exactly. And because if you want to be able to accept a pattern like this from an untrusted source, or even a pattern that you haven't fully vetted, and someone could send you just 26 characters and cause you to spin for 11 seconds, that is a denial of service attack. That's a RDoS, a regex denial of service. Now, .NET has had backtracking engines since .NET began in 2001, 2002, and they are super powerful. There are things that you can do in a backtracking engine that you can't do in a non-backtracking one. For example, you can do back references. You can say, I'm going to capture some text, and then later in the pattern, I want to match the exact text that I matched earlier. It's called a back reference. Super valuable. Difficult, if not impossible, to do in a non-backtracking engine. So there are lots of good reasons to do this, and they can be super fast, especially for successful matches or even average case matches on most patterns. But they have this worst case behavior that is really problematic.
So this isn't a computer science question now. This is a program management question. Should this be allowed? That's a very binary, either backtracking or non-backtracking. Or what should it do if we've noticed that we're getting ourselves in this situation? Is there some kind of a rails we could put on this to say, throw an exception, get out of there, 2 seconds was too long?
Exactly. I love that you selected seconds, because that is what .NET has done since the early days of .NET. There's a timeout parameter that's passed here. So I can say timespan from seconds. I think you used 2. So I'll say 2. And now when I run this, we see it's going. But this next one, when it trips over 2 seconds, now we get an exception saying the regex engine timed out while trying to match the input string. So it's a guardrail that's in place to handle that. So this has been sort of...
Is there a default one, though? You had to put one in there. What's the default?
The default is infinite.
Yeah.
Yeah. Now, it is overridable. You can set a global timeout so that any regex pattern that hasn't explicitly specified it will then pick up that global timeout.
Right. Which could be helpful if you had legacy code that is out there that you don't want to mess with, but you do want to say, we have an issue, we know it's there, we're going to put a top end on the number of seconds for the entire
However, so this is a perfectly valid thing to do. There are very good reasons to use a backtracking engine. They're can be super efficient, really good performance, other than these worst case cases. But if you do want to accept untrusted input or something that might be problematic, you have 2 escape hatches in .NET. One, you specify a timeout. The other is, as of .NET 7, we added the 4th engine that I was alluded to earlier, which as the name implies, is a non-backtracking engine. And if I run this, now I don't have a timeout at all. We see it again blazes through the whole thing, because this engine guarantees linear execution in the length of the input. So assuming it could successfully construct the regular expression, which it couldn't if you tried to use a back reference or something like that, it will now provide you with a guaranteed linear throughput regardless of what input is thrown at it. And you can see we've avoided that exception as a result.
Now, I noticed that it blazed through it. That's because it has an entirely different path, but is it possible to write a regular expression that the non-backtracking engine would say, I can't do what you expect me to do because in order to do that, I would need to backtrack?
It will never, well, yes. So let me just, for fun, let me just add in here /1. Which says there was a capture group here. This is what's called a back reference. So whatever matched here, I want you to match the same thing here. And if I try and run that, this will blow up saying back references aren't supported. I can't I can't do what you're asking me to do because it would have required backtracking.
Excellent.
And so if you're able to successfully construct the regex instance, then you're guaranteed that sort of linear behavior. And there's only a few constructs that you can't use. You can't use back references. There's something called conditionals in the .NET regular expression language. There's something called lookarounds, look-aheads, look-behinds. That's sort of and also atomic groups, because they have subtly different semantics. Everything else you can use, but those specific things will fail with this engine. Now, this engine isn't always faster. In fact, in many situations, it'll be slower than the backtracking engine, but you get guaranteed worst case behavior. So if what you care about isn't utmost throughput on good inputs and good patterns, but that I don't take down my server, this is a really useful tool in your tool belt.
So I've got a couple of questions. First, in this case here, you are making 40 different regex instances with 40 different inputs. Mm-hmm. If you were not, is a best practice to store the regex in an instance outside of the scope?
Absolutely. So in general, one of the most expensive things with a regular expression with a regex instance is constructing it, because it's parsing the pattern and it's doing analysis to transform the tree. We saw it. There was a greedy loop in our A star B, but somehow it magically became an atomic loop instead, meaning one that doesn't backtrack. That's because the analysis engine looked at the pattern, and then if I'm using compiled, we're using reflection emit to create a brand new dynamic method that has to be JIT compiled. Like, there is a whole bunch of work there associated with it. So you absolutely, whenever possible, want to have a static my regex that has your pattern in it. And you remember from the source generator, the source generator does that for you. So let me see if I can just Control Z back to my source generated code. In the generated field, there we go. We saw that the demo method is just returning this demo instance 1, and we can see that here that's just a static read-only field. So it's implementing a best practice by storing that for you. In fact, if I were to come in here and I were to, in a completely different class, example 2, demo 2, but they're using the same pattern, and I go look at what this is doing, we can see it's returning the exact same instance in both cases because it recognizes they're same. So I'm just going to use that single cache singleton to implement this. So it's caching for you. If you're doing it yourself, then you should absolutely cache it whenever possible. There is some of the APIs will try and do that for you. So there are static methods on regex. So I can say, here is my input, and try and look for my. So under the covers, this will use a recently used cache. So it's cache 15 or 30 different regular expression objects, and if it sees that this pattern with the provided set of options match one of the things in its cache, it'll just use it. Otherwise, if the cache fills up, it'll ditch the least recently used thing. But in general, you're sort of at the mercy here of what else is going on in your program, and so it's better to just cache it in a static yourself. In fact, if you're not using non-backtracking, well, even if you are using backtracking, if you can use the source generator, just use the source generator and let it do the caching for you. Don't worry about it. Just let it take care of it. The only time you can't use the source generator is if you don't know the pattern at compile time. So if you were dynamically generating your pattern based on something you read from a localization file or some input the user provided, which would be very dangerous, at least with backtracking. Unless you're doing those kinds of things, just use the source generator.
Okay, so let me ask you something as we get towards the end here, because people are thinking about now the implementation of how these things work. We've done fairly simple examples, although backtracking is somewhat complicated. In Teams just now, I pasted to you a simplified email regular expression. Let's dissect that and its implementation. It looks, it'll look a little bit threatening, as regular expressions somewhat do. And one of the things that I want to ask kind of more as a best practice for application developers are, what's the right way to have a good regular expression for common types, short of Googling for regular expressions and hoping that the one you found on the internet is a healthy one, a good one? Like, does Microsoft or does .NET include best practices for email or for, I don't know, social security numbers, data types that we might recognize? We
don't have any of those built in. There are NuGet packages where others have provided. I think we have some examples in our documentation, but we haven't, to my knowledge, we haven't blessed any as, yes, this is the one you should use for this particular concept. All right, so this is what you wanted me to look at.
Okay.
So we get the nice syntax highlighting. We can see how the engine has, it'll explain what it is. So we can see that there's a hat there at the beginning. So we're matching only if we're at the beginning of the string. Then we're matching a character in that set. You see it even though we've specified a normal loop, it's automatically converted to be atomic because it knows that that's okay. And it's saying at least once, because the plus sign means at least once, whereas the asterisk means any number of times, including 0. Then we're matching the @ sign. Then we're again matching that same set of characters. But now you can see, because of what comes after it, because this character class includes a period, and what came after the loop was a period, this can't be converted into an atomic loop anymore. So we saw that that one's now greedy. Then we're matching a period. We're matching any letter from the English alphabet, at least 2, up to 4 times, and then we're matching at the end of the input. So we can go and look and see exactly what that looks like in the source generator. The main loop here, or the main entry point here, is the scan method that gets generated. And because the pattern started with an anchor, this doesn't need to be a loop. If I went back and I removed this anchor, now we can see that there's a loop here because there are many possible positions that it could match. But with the anchor, the source generator recognizes that this can only ever match at the beginning of the string. So confirm that we are, in fact, at the beginning. And the analysis also indicated, because this had to match at least 2 times, because there was a character here, that's 2, that's 2, 3, there's an @ character here, that's 4. This has to match at least once, that's 5, and this has to match at least once, that's 6. So it recognized that any possible match is at least 6 characters long. If the input was 5 or fewer characters, fail immediately. There's no point doing anything.
Right. And those things are subtle. Like if you look back at the regular expression, it's matching the top level domain, and it's assuming incorrectly the top level domains are 2 to 4 characters long. So like .ninja is a valid domain now, and .microsoft, and those are not represented here.
Right.
Those little kinds of things are very subtle business logic issues that you're only going to catch through a great deal of tests.
And if I had it expressed this way, and I just start debugging through it, why isn't this matching? And I get to this point, I say, why is it checking for 6? Oh, yeah. I get it. So once we know that we're at a valid point, then it calls this try match current position. And this is where this is, okay, I found a possible place that I could match. Now let me actually perform the whole thing. And now this breaks down very much like if we were just sort of look at each individual piece, we can see how that code translates here. So match, if we're at the beginning of the string, is pos equals 0? No? Bail, we're done. Match a character in the set, this atomically at least once. And this also highlights how we can take dependencies on functionality, optimized functionality elsewhere in .NET, and just use it as part of the regular expression engine. So this overload of index of any except takes this type called search values, which was introduced in .NET 8. So this code looked different in the source generator with .NET 7. You upgrade to .NET 8, and now the source generator is able to take advantage of stuff that's in .NET 8, including the search value thing. This search value instance, if we go down and look at it, says this is searching for characters in or not in, and it's listing out everything that is matched by what you had expressed. And you can see it's just creating the search values.create, which anyone could do themselves, but it's using that here. And what this does is there are 15, 16, 17 different implementations under the covers where search values.create will examine this effectively as its own little language and create an optimized implementation that's able to search as quickly as possible with vectorization, SIMD support based on whatever you currently hardware you have, and AVX2, AVX512, ARM intrinsics, whatever, and it'll try and create an optimized way for doing that search. So we're taking advantage of that up here in, where was I? In here to say, find all of them. So we're looking for the first thing that isn't one of them, hence index of any except, and make sure that we got something. If we didn't find anything, then it didn't match because it had to match at least once. And then we're using spans here very liberally. The input to this is a span, and we're just slicing as we go, slicing through the span. So then we're checking for the @ sign. Is the next character not? And you can kind of get a sense for how this progresses. There's this very nice translation, and hopefully, even though the code is machine generated, it's pretty readable and pretty understandable what's happening. Now, the complication, to your point, does come into play when we start having backtracking. You can see, for example, now that we're matching a character in the set here, again, we're trying to match as many as we can, but then we jump ahead and we set things up such that if we fail, we then backtrack to this location. So there are go-tos in this generated code, whatever your thoughts on go-to might be, because if something fails to match, if we can't find the period that we were expecting, let's backtrack. So we jump back to this location. You can see we're checking for those timeouts. Because anytime we backtrack, we want to make sure we're not doing this catastrophic backtracking. And then we try and back up to the previous place that could have matched. So again, taking advantage of these built-in operations, we just use this vectorized last index of to back up to the next possible place it could have matched, and so on.
See, say what you will about go-tos, but you can't argue with a go-to that has 40,000 unit tests backing it up.
That's right. So that's the basic idea, and you can, the whole system is built in this fashion.
I think another little nugget that was kind of genius that was snuck in there was this idea of the actual chipsets and the remembrance of how deep the stack is. If we go back to that example from the very beginning of our conversation an hour ago, where we saw Kernighan giving you, Rob Pike's, here's this much, here's 100 lines of a basic regex. And now we have an optimized stack in .NET 8 that knows about ARM, knows about 10 different flavors, 6 different flavors of Intel, and checks for correct instructions to do the right thing. We're sitting on top of span of T. We're sitting on top of an optimized multiple, what's the new jitter? I forgot the
dynamic PGO. Is that what you're referring to?
Yeah. Dynamic PGL. And then of course, you just type a string with ABC in it, and you gain the benefits of all of that. It will run as fast as it can on your processor.
And every time we release a new version of .NET and we add new support, we then can take advantage of it, and it all just happens under the covers. So you mentioned dynamic PGO, and you saw in the code we were just looking at, there was that timeout check. Well, the way it's set up, if I go back to the code over here, you see there's this line here that says, do I have a timeout at all? And it's checking to see whether the timeout that has been set is infinite or not. If it's still infinite, this ends up being false. It's a static read-only bool. When the JIT compiler recompiles at tier 1, it will treat this as a constant. And that means anywhere this shows up, all of these checks completely disappear from the code, because it just gets optimized out. And so we're able to benefit from those kinds of improvements.
Right.
Another example, you see us using search values. Well, in .NET 9, there are more things that we can do with search values. There's now a search values, we can use string to search for multiple substrings within a search. And so if you have Scott or Steve, we can do that search with a search values in an optimized way using some really clever SIMD tricks. It's beautiful.
And just a couple of quick notes as we head out, because we tend to use TLAs, 3-letter acronyms, right? Where we're talking about the jitter, the just-in-time compiler, and then profile-guided optimization, PGO, which is an extension or a new version of tiered compilation, which is I did it as fast as I could, and I think it's pretty good, but I'm going to give it another try or two, and I think it might even get better. The more times you let me run this, the better I'm going to let it get. Which gives you the benefit of
from a previous compilation to impact the next compilation. I also use the word SIMD, single instruction, multiple data, which is instructions on different kinds of hardware that allow you to, in a single instruction, do the same operation across multiple pieces of data. So rather than checking whether just one character is the letter A, I could check whether 8 or 16 or 32 characters were the letter A.
Fantastic. This has been a fantastic conversation. I really appreciate you taking the time to give us all of this knowledge, and I appreciate you and to the team that's making this kind of stuff work. I feel like now I much, much, much better understand what's going on when I write a regular expression. And now I can see that I can introspect into the code and see exactly what's happening. This is a reminder to all of us that computers are not a black box. You don't just have to put a magic string and then just hope it works. You can dig in, you can debug into that code. So thank you very much. We'll have you back very soon to talk about more internals. We've been chatting with Stephen Toub all about regex inside of .NET.